Good. Good morning. Good afternoon, class. For today, we're going to continue our discussion on transformation of equation. And I mentioned from previous lecture that we are going to go back to the calculation of theta sub s, which is this guy right here. Now, first, how can we calculate theta sub s? So again, theta sub s is a rotation of your stress element when you want to reach, for example, your maximum in plane shear stress. So now, theta sub s can be obtained using equations, and you can obtain it using more circle. I'm just going to put circle here. So you can calculate it equation or using your more circle. Now, once you calculate it by equation in Mohr circle, you will find out that your theta sub s absolute value plus theta sub b absolute value is equal to 45 degrees. Now, I do not advise you to use this equation here to calculate for your theta sub s. This is just to confirm that your numbers are accurate. I'm going to explain you why you should not use it. So let's say we have a Mohr circle. Let's say you have a Mohr circle. And in your Mohr circle, let's say you have these two components. Still see it, okay? And then you draw your circle. Now, you connect this line, and then you need this counterclockwise rotation in order for you to reach your minimum and maximum stress. So let's say you want this point, so you need this rotation. And let's give a number. Let's say this is 20 degrees in counterclockwise. So let's say that's 20 degrees rotation. Now, that would be your theta sub b, which is positive 20. Now, your tau maximum is this rotation here. So that's your theta sub s is rotation in your your clockwise direction. So that's a negative number in this direction here, which means that, I'm sorry, this should be 10 because that's, oops, that should be 10 because that's 1/2 in Mohr circle. Now, if this is 90 minus 20, so let's say that's 70 degrees. So that's negative 70 degrees in order for you to get your maximum shear stress. Take note that once you rotate counterclockwise, you will reach these positions here of this given sigma x and sigma y because they are equal at maximum shear stress. Now your theta sub s is equal to negative 35 because that's twice, right? So if you're going to total them, absolute value, that would be equal to 45, right? But the problem is, let's say you don't want to perform Mohr circle. I don't want to do this. Let's say I don't want to do this. I'm just going to apply my equation, which is theta sub s plus theta sub b is equal to 45 degrees. And that's absolute value. Now I know my theta sub b is 10 degrees. If I'm going to calculate this one, I'm going to get theta sub s, which is equal to 45 minus 10, and that's 25 degrees. And you don't know if it's positive or negative. You don't know the rotation. So don't use this equation alone as it is. You have to use either equation or Mohr circle so that your answers would be consistent. The problem is once you get this absolute values here, you now don't know if it's negative or positive side. So just want to make sure that everything is accurate. But yeah, so that would answer that theta sub s question last time. And that's really important if you are doing those calculations. So again, don't use this alone, this theta sub s plus theta sub b to calculate your theta sub s. You may get the right answer, you may not get the right answer. Just use transformation equation or Mohr circle. Of course, it's just either of the two if you have an exam or a question. Any related questions associated with theta sub s? And I hope that's clear. And that's a pretty good question. To be honest, that was not asked to me in the last 2 years about that equation there. And again, I do not recommend you to use that equation. Just stick with your equations, stick with the Mohr circle, and use this just to check your answers. Question? Okay, so I think we're good, and I hope we're good. Okay, so now last time now we already know how to calculate our stresses at a certain rotated axis if using transformation equations which we derive using Mohr circle, which I also showed you how a Mohr circle works. And now we go back to our 3D problem last time, which is this guy here. So let me that slide. So please practice these problems. Not this one. So I asked you to practice for this problem, but I have the answer here. And everything is uploaded on D2L. Now we stop somewhere here. So let's say we have this particular problem. We have a component. So the axle of an automobile is acted upon by forces and couples shown. Oops, I don't have the. So that's your axle is acted upon by forces and couples shown. So those are the forces, 3 kilonewtons aligned along Z. So I gave you this axis here along Z, that there's another 3. So knowing that the diameter of the solid axle is 32 millimeter. So once you slice it around H, this would be the cross section of your material. Determine the principal planes and principal stresses at point H, located on the top of axle, that's the top, and the maximum shearing stress at the same point. Now, the first thing is, how would we know the principal planes and principal stresses? We do not have a stress state yet, so disregard this one on the top. I should have an animation for that, but yeah, it's gone for some reason. But if first we have to obtain what would be the stress state at point H. Now I have an axis here, so you have to look at the XY plane. So you are looking from the top. Now, if you are looking from the top, so let's just write it here. Okay. So if you're looking from the top, so let's say, I'm picking the wrong pen again. So if you're looking from the top, so that would be your, let's say your Y, and this would be, for example, your X. So that for your X. So this is point H. Again, you are sitting on top, you are looking at point H. So now, remember that we have a force couple system in order for us to determine the forces at a certain point if we have a 3-dimensional object. So we have to get the rotation in X, Y, and Z at this specific spot right here. Now, if you are analyzing this axle right here, your reference point would be the center of that of this component here. So if I cross section this one, I have H on top. I have this C as a center of my object. Now, first, let's look at rotation in various directions. So the technique right here, if you have a 3-dimensional, is look for rotation in all axes. That's the first step that you have to do. So rotation in X, Y, and Z. That's the first thing that you have to check. What's the rotation? Is it moment? Is it torque? Now, if we look at X, so now let's first do X-axis. So if we are going to do X-axis, so imagine rotation in X-axis, you are sitting right here. If you are sitting right here, you are looking at Y and Z, which means if I'm here, I'm looking at plane Y and Z. So that's my view. And let's say my reference point is H. So I can see my component as something like that. But I have 2 different forces, which are 3 kilonewtons each. And it has a certain distance from point H, which means that these 2 forces, 3 kilonewtons down, 3 kilonewtons up, is producing a rotation along X. And what would be that rotation? So if I'm going to calculate for my rotation, my m sub x is equal to, so this 3 kilonewton here, if you are looking from x, so it's producing a rotation which is counter clockwise. So this 3 kilonewton here is producing counterclockwise, which means I'm going to get a value of a positive number, which is 3 kilonewtons times its distance. So the distance is 0.2. So that's 0.2. Now, what would be the rotation of this 3 kilonewtons here? You have 2 looking from x. So you can see that the rotation from point H going into this 3 kilonewton is now clockwise. Now, since this produces a clockwise rotation, that's a negative number. Just checking if you can see that. Let me know if not. And so that's minus, I'm just going to write below, 0.35. So that's the total of this 2.2 and 0.15. And take note, that's a minus sign times 3 kilonewtons. So now your moment in x would be equal to this rotation, which is negative. So again, take note that I didn't put negative here because I provided the direction, but your m sub x is negative, which means it's clockwise, negative 450 Newton meter. So that would be the rotation in x. Now, you have to analyze for each axis. We're done with x. Let's look at the y direction. So what would be the rotation in y? So now, if you are looking at the rotation in y, you are sitting, let's say, along the axis of y, you are looking at plane x and z. If you are looking at plane x and z, you will see this one as just a circular cross section. So, so if you are going to write the axis x and z, so you are now at rotation in y, you will see this cross section, which means that you are not really producing a moment, you are more producing a torque. Now, you have a given torque, which is 350 Newton meter. So that's straightforward. There's a torque or there's a rotation in y. So you know that your torque, which is along y, and that's already given, is 350 Newton meter. Now, the question here is, does your two forces provide a rotation along y? And if you are looking at these forces, these 3 kilonewton forces, they are located, they are situated like this, which means they are acting perfectly at the center of your cross section. It will not produce a moment or a rotation along your y-axis, which means that there's no rotation in y except for this given torque, which is 350 Newton per meter. So that's in y. Now we go to z direction. So if we go to z direction, in z, so you have to do this one by one in order for you to avoid mistakes. So let's say let's just assume we are sitting from top, not exactly that. So we are sitting from top. We are looking for x, y, or looking at a plane y and x. So rotation in z is, that's your y, that's your x, and you are looking here. So that's point H, and your object looks something like that. Now, if you are looking at z, these two forces appears as a point, not an arrow anymore. So if you are looking at those points, so those are the forces located around here. So it's either towards your paper or going going out of your paper. So you have 2 points, which doesn't really produce a rotation in z-axis, which means your m sub z is, z is equal to 0. Now, I can now combine this moments or this rotation and then put it at point H so that we can determine what would be the stress state at point H. So now, if we are going to simplify the effects of these forces and torque, we are going to write this one as this on your lower right side of the slide. So you have rotation along x. Again, clockwise, this is a torque counterclockwise, which is given right here, which is a positive number. Now, the question here is what would be the stress state at point H, and you are looking from top. Take note that you want to get. Yeah, go ahead.
I have a question. First of all, good afternoon.
Yep, yep.
Second of all, for rotation in Z, one of is not one of the forces should be an X, right? Technically, because you drew 2 points implying that they're
Yep.
both
One is
upwards, but
X.
one should be just a minor detail, but just want to be sure that I'm understanding it correctly.
Yes.
And
Yep.
so because of that, and well, it wouldn't matter anyways. There is no, even if there weren't X,
Yep.
even
So
if there were both dots, it would
yep.
still not matter for the
Yep.
rotation instead.
Okay. Yeah. So one would be X and what
Get?
would be dot. Yep. Yep. That's true. Yep. That's correct.
But
Yep.
and it wouldn't, in any case, it would not affect the rotation instead,
Yep.
given that it's not going to cause any turning. Okay, thank
Yep.
you.
That's correct. Yeah. But one is X, one is dot. Yep. Yeah. Thanks. Yep. Any other question? Okay, yeah. So now let's go to, but yeah, again, just let me know if you have any question. I'm trying to slow down here. Again, this is one of the, uh, most of the mistakes comes from this analysis for sure. But yeah, so now we are looking at H. So we are looking at Y and X. So if we are looking at point H, so that's your point H. Now this would be your Y, let's say, and that's your X. Now, if we are looking for the effect of your moment, so your moment is rotation along x, which means that if you can imagine this section here, your rotation in x is from this point and it's rotating towards that point, right? So the rotation is like this. So it's rotating clockwise, it's negative number from this point up to this point. So it's pulling an element from this side, from the lower side of your axle. It's pulling it and pushing it going into your H, which means if we look at point H, it's pulling here and pushing it right there. It's producing a compression along y-axis, correct? Now, if we change the moment direction, of course, that would be a different story. This would be tensile and that would be compression. So your signs for your moment is very critical if it's rotating clockwise or counterclockwise. So again, from this point, so your rotation in X along X axis is clockwise. Now, if you cross section an area along your point H, this would be this point right here. Your rotation in X axis is this rotation here. So you are pulling from this lower side and pushing it at point H. So if you are pushing at point H, your moment produces a compressive normal force along Y, right? Which means I can say that my sigma Y is equal to mx mc over I. So that would be to convert your moment, the effect of moment, to your normal stress, or the dependence of your moment to your normal stress at point H. So you are going to get a stress which is in compression. So you are compressing H, and that would be your sigma Y. So that would be for your moment. Now, how about for the torque? It's given here 350 Newton per meter. Now, your torque is, if you are looking at point, if you are sitting along the axis of Y, you would see that your torque is rotating counterclockwise. Now, rotating counterclockwise, so if you're going to project the y-axis here, so that's your y-axis, it's rotating counterclockwise, which means if you are looking from the top view right here, it's producing a stress similar to this one. So let's say that's your H. So it's producing a shear, which is this position here. Now it's rotating counterclockwise. You look at point H, you look from the top, And then now you can see that this rotation here is producing a shear towards this part right here, because that's the whole section of your axle, and the torque is moving towards this way. So that's applying a shear, which means if I'm going to draw my element here, so that's the view of my element from this one. So it's producing a shear which has this component here, which is a positive shear. Now I have now a shear component, and I don't have any X. I don't have any stress along my X, because I have one moment which is producing a stress along Y, a normal stress along Y, and I have a torsional stress or torsional load which is producing a shear at point H. Now I can then write my I can now write my tau as, or tau xy in this case, as T C over J. Now we can now calculate for our stress, which is written here as MC over I, and now we have tau, which is tau xy TC over J. Now if we calculate this value right here, that would give us a value of yeah, I think there's someone raised his hand. So okay, yeah. Okay, sorry for that.
Yeah, so I was just wondering, why is it tau xy and not tau xz?
Okay, yep. So right now, that's a good question. In this particular case, and that's not normally it's not clear in the book. We are looking for tau x stress along tau xy along this plane xy right here. So so for example, we are asked to principal stresses at point H located on the top axle. So we are looking from the top, and we assume the axis X and Y right here.
Oh, okay, thank you.
Yeah, but if we are looking from the side, yeah, you would imagine that it should have a shear stress along Z. So it would depend on, for example, the direction that it was asked. It will be asked, but for your exam, I'll be clear with the direction in which plane you are going to analyze it. But yeah, that's a good question. Yeah, thanks. Any other question? I think there's one more.
Yeah, Professor. Yeah, I was wondering. I didn't quite understand how you got it as a positive shear.
Okay. Yep. Okay, so let's repeat that again. So remember that we have a different convention for positive and negative shear. So this would be the components for our positive shear, and this would be the component for our negative shear. Oops. So that's a negative shear, and that's a positive shear. Now, once you have those shear components, we look at the at our element again. So take note that if we are rotating, let's say counterclockwise, it's if you are looking at point H, it's producing. So let's say that's H, and that's part of your component. That's your cylinder. If you are looking at the top, so this is top view, and then if you have a torque, that's the direction of your shear in your counterclockwise torque. Now, imagine that if it's not counterclockwise, it's clockwise. So you would imagine that the arrow would be the other way, right? So if you are rotating clockwise, you are looking at point H, you will produce this shear at point H, which is a negative. So how did I find it's negative or positive? If you look at this one, this is consistent with this. If you look at this one, that's consistent with your negative shear. So that's why I found out that based on this loading condition, it gave me a positive shear. That's clear, or?
Yeah, I think it kind of makes sense. So wait, the bottom part of the edge, is that like okay, I think I kind of get it.
Okay, and imagine, take note that class and everything, although we are applying torque, we are assuming that everything is in equilibrium. We are not actually moving the object, so that's why we have to balance out the forces there. So yeah, okay. Next question, Alex.
Hello, Professor.
Hello, yeah.
I understand the positive and negative sign conventions for the
Okay.
shear, but for this specific question, given the way we have our axes drawn below, shouldn't
Okay.
we reverse the signs? Like, should we not be looking at this from the bottom?
Okay. Which one? This. Okay. Sorry.
Like on the right where you drew the black arrow pointing to the left for the
Okay.
clockwise rotation,
Okay.
that's on the positive Y face, but it's pointing in the negative X direction. So should it be negative shear?
Yeah, that's a good point. I think I should have written this X on the other side. That's. I think. Yeah. Yeah. That. Yeah. That's. If I'm putting this X on the other side, that's my positive direction. Everything would be correct. Yeah. Right.
Yeah, I think now it makes more sense.
Yeah,
Connected.
for me, I made that mistake. I didn't mean to do this one as positive and negative, to be honest, when I first did this one. I just want to put the reference axis, but I should have put which one is positive and negative, and that should be a negative x right here. If I just put it on the positive side, yeah, that would make sense because it would confuse you with directions. But yeah, that answers your question, Alex. But I'm going to fix this and re-upload this slide. I found some minor mistakes from the last time. I'm going to re-upload this set of slides over the weekend. But that answer your question, Alex?
I think so, yeah. So in my notes, I've been trying to draw the problem and follow along. So I should just switch the direction of my axes, like swing the X around to the other side.
Other side, yep. But I should
Oh.
have become this clear. Yep. But yep, thanks.
Okay, thank you.
Okay, any other question? And again, your positive x is on the other side. That's my assumption, but I'll make it clear. And if I made a mistake normally in the exam, I own my mistake and I give a perfect score for that item. So if I made those mistakes, I'll own it for sure. But I hope I would not make any mistakes. But yeah. Any other question? Okay, just checking if. Okay, I think everything is clear. Okay, so now let's go back to the problem. So now we know that we have tau xy and our normal stress. We can now calculate for those values. So let's do that. So, okay. So I have lecture here. So now we have torsion, which produces tau xy, and that's Tc over J, and that gives you a value which is okay. So okay, I'm just checking my notes here. Sorry. So that would be equal. So if you're going to the equation for J would be pi c raised to 4 divided by 2, and that becomes 3. And then once you calculate it, you're going to get 2t divided by pi c raised to 3, and that would give you 2 times your torque, which is 350, and that's your torque, Newton meter, divided by pi. Now your c is given in a problem, so take note that it's given separately here as 32 millimeter. And then I'm going to divide it by 2 because it's diameter, we need the radius. Take note that your c is radius, so I have to divide it by 2. So that would give me a 0.016 meter, so I converted it into meter. And 3, and then my tau xy would be equal to 54.4 MPa. So that would be my answer for my tau xy. Now, if we go to our normal stress, which is sigma y, so we don't have any sigma x. There's no sigma x. We only have sigma y. So that's mc over I, and that's equivalent to, okay, so my I is pi over 4 c raised to 4. So I can put 4 right here. So I can just substitute the values there. 16 meters square. Or sorry, that should be cube. Cube. And then I have, okay, negative 450 Newton meter. And that would give me sigma sub y, which is equal to negative 139.9 megapascals. So, yep, and that would be sigma y, and you know that sigma x is equal to 0. So that would be the starting point for your stress, and then you can now calculate your principal stresses and maximum in-plane shear stress based on the following. So now, if I have this loading condition, I'm going to get this stress state here. So I have a compression along y, negative 139.9. I have tau xy, which is 54.4 positive, and I forgot the line here. Again, everything is a little bit messed up, but yeah, so your sigma x is equal to 0, which is along x. Now, but the question is not about your stress state. The question is the principal planes and principal stresses at point H. We have two different methods. Either I could use equation or I could use Mohr circle. So let's use equations for this one. So for equation, first let's calculate theta sub p. And that's the question associated with principal planes. What rotation do I need in order for me to reach my principal stresses? And if you look at your equation, the equation for that is tangent to theta sub p is equal to tau xy divided by sigma x minus sigma y divided by 2. And that would be equal to, okay, let's just substitute the number 54.4. I have 0x plus, so because it's negative, it becomes plus 139.9 divided by 2. So, and then once you calculate this number, it will give you a theta sub p, which is equal to 18.9 degrees or 19 degrees if you want. But that would be 18.9. So that would be my theta sub p. So that answers this question here, principal planes. How about principal stresses? So now let's go to principal stresses. So I would need my minimum and my maximum number. So here, so sigma mean and max is equal to, if you can still remember the formula, that's sigma x plus sigma y divided by 2. That's your sigma average plus minus. So plus is for maximum, minus is for minimum. Wait, I cannot see it. Okay, I don't know if you can see it or not. Anyway, yeah. So let's scroll here. Okay, so that's plus minus square root of sigma x minus sigma y over 2 square plus tau xy square. It still fits. Okay, and that would give you, so you just have to substitute 0 and 139. So that's 0 minus 139.9 divided by 2 plus minus square root of 0 plus 139.9 becomes plus because it's a negative sign over here. Oops. Divided by 2. Everything is raised to 2 plus 54.4 raised to 2. And that would give you a value of negative 69.95 plus minus 88.6. If you remember your Mohr circle, that's your average and that's your radius. Average plus minus radius, but just have to stick with the equation so that everything would be consistent. But yeah, your sigma maximum will then be equal to the plus, this plus sign here. So which is this plus sign here. Oops. Okay. So which means 18.65. And then that's megapascal. Don't forget the unit because it's a stress. And your minimum is equal to negative 158.55 MPa. So that would be the principal stresses, minimum and maximum at point H. Now, there's also a question. So we're done with letter A. We can now go to letter B. So for letter B, we're asked to calculate for maximum shear stress at the same point. Now, maximum shear stress, I would say in plane. Again, I'll be clear in the exam. This should be maximum shear stress in plane because our next topic is tau absolute maximum, not in plane. But so the question here is what would be the maximum in plane shear stress? So if we are going to use the equations here, so if you go back to our previous slide, the equation for in plane or in two-dimensional analysis, maximum shear stress, you're going to get square root of sigma x sigma y over 2 squared plus tau xy squared. And if you can still remember for Mohr circle, that's just your radius of your Mohr circle. That describes the radius of your Mohr circle. But this is for equation, so we have to substitute the number for sigma x, which is 0, plus 139.9 becomes positive because it's negative number, squared plus 54.4 squared, and that would give you 88.6 megapascal. So that would be your tau maximum in plane. So now we have this as maximum in plane. We now got our principal stresses, and we know what would be the rotation or the principal planes associated with your principal stresses or the rotation that you need to obtain those mean and maximum. Any other question? So now that's for equation. How about for Mohr circle? I'll be quick right here for a Mohr circle. I'll go back to this slide right here. So let's so if we're going to solve this by Mohr circle, so we know that our tau xy is positive 54.4. We have 0 stress along x. We have negative along y. It's compression with this number. Now, how can we do it in Mohr circle? So first, you have to locate the center of your circle. This is the intersection of your axis, not the center of your circle. So how can I get the center of circle? So let's do it quick. So this is method number 2, which is Mohr circle. And sorry for my handwriting. Okay. Okay, now, so for method number 2, so again, first thing is locate the center of your circle. And that's just your sigma average, which in this case, the sum of x and y over 2. And so you have 0 and negative 139.9, and that would give you negative 69.95. Now, if you're going to draw the center of a circle, it would be negative 69.95 and 0. That would be the point in your coordinate system, and that would be this point right here. So it's in a negative axis. Now, second is plot your point. So plot sigma x negative tau xy. So how can I plot that one? So sigma x is 0, negative tau xy is negative 54. So I'm going to have 0 and negative 54.4. And if I'm going to plot that, that would be this point right here. Now, the third is plot sigma y positive tau xy. So you have two different set of points. So now this 54 becomes positive, and then what you will get is sigma y, which is negative 139 and 54. I'm going to write it here. So negative 139.9, and you have 54, which is now positive. So you have 2 points. Now you'll get this point right here. Now you connect them, and then you can now get the radius of your circle. So if you get the radius, so the radius is this guy here. I think that should be here, V right here, but you can see that this would be this triangle right here. So your radius is this hypotenuse, which is A, from A up to this B point right here. That B should be here. I don't know what happened to my file. It was working well when I tried it. I think I pressed something that messed up some of my animations, and position of points. But if you're going to get the radius, so the radius would be equal to this square root of the square of this point, which you know it's 69.95, and this is 54. So square root of the sum of the squares of AC squared plus CB squared, and that would be 69.95. Again, we are not accounting negative here. It's just dimensional analysis. We just want to know what's the dimension of this radius here. So, and that's 54.4. Yep. Square and then square root. Maybe you can't see it. And your radius would now be equal to 88.6. Now, if your radius is 88.6, I can now draw my circle. So I can now draw my circle. Now, once I draw my circle, I know the intersections along my x, and that's my minimum and maximum. So I would find my minimum and my maximum, which in this case, you can see that your maximum is radius, which is this portion right here, minus AC, minus this small section, and that would give you this distance from the intersection at 0 position at that point. I will not be too detailed. You can do a little bit of practice here, but your sigma maximum would be equal to 18.65. Now, your minimum is right here. Your minimum is the radius, which is this radius right here, plus AC. That's this. So that's a distance from this point, and that would give you negative 158. 158.55. And again, that's in megapascal. So don't forget about that. I forgot, but don't forget that one. Now, so that would be for minimum and maximum. And you can see that that should be consistent with your equations on top. And I just want to check if that's consistent. And that should be consistent on the top right here, which we used equations. Now, moving again here. So we have maximum and minimum. Number 7 would be your, let's say we want to calculate for our, the next question I think is theta sub b, sorry. So now, next question is theta sub b, which is part of question A. So that would be this rotation here. So from this point, we want to reach our maximum, so that would be this angle. So if we are going to calculate for theta sub b, we are analyzing this dimension or this right triangle here with 2 theta sub b. And the rotation is counterclockwise, which means it's a positive angle. So if we are going to calculate for theta sub b, so tangent to theta sub b is equal to your opposite CB. So that would be CB divided by AC, and that would be 54.4 divided by 69.95, and everything here is based on dimensions, and you will get a theta sub b, which is 18.9, and that's a positive or your counterclockwise rotation. Now that's theta sub b, and the last question for part B is what would be the tau max. Now, if you have a tau max in plane, we know that this is just equivalent to your radius. And that's just this maximum of along your maximum value of your tau, which is this points here, which that would be your tau maximum in plane, and that's just equal to r. And your radius, of course, you already calculated it from top. It's 88.6 megapascals. So that would be the answers if you do more circle. So that's the tau, that's the angle, it's positive, it's this one, and that should give you the same number. If you go right here, so that would be the same. Okay, any question for this point? Now that we answered it using equations, using Mohr circle, this problem. So I'm going to go back to the slide because the next slide is somewhat important. So we solve it, method 1 equations, method 2 Mohr circle. So now I'm putting this axis right here, even in your exam, maybe not in your book, or maybe not at all, not putting the axis. It's assuming that this is your convention and that's what it is. But just showing you that what if I switch my x and y? If I switch my x and y, and again, this is not referring to positive and negative. I'm going to fix that and re-upload this slide. So if I put this one as x, I put this one as y, if I solve my problem, I'm going to get this stress state here, which has now a different values, or at least directions from my shear and from my normal stress. So that would lead to a different answer, not entirely different. It's just positive and negative, but that would confuse you once you're doing sample problems. And most of the time, the concern really is it positive, is it negative, and sometimes it could be a headache to determine which one is which. But just to show you how important the reference axis is, and again, in your exams, I'm going to put a reference axis so that everyone would have the same answers and we don't run into trouble of like one is positive, one is negative, but it's just a matter of putting some assumptions right there. Okay, question? Okay, so
Yes,
now,
Professor.
yep, go ahead, yep.
So if the question asks to find the theta of S, so do I just use the formula theta of S plus theta of P equal to 45, or that would be wrong?
That might be correct at some cases. That might be wrong in some cases. So I would suggest you to use equations if you're going to calculate for theta sub S, or if you are going to use Mohr circle. So if we go back, for example, here. So if you this angle here, oops, is your theta sub S. Oh, sorry, theta sub P. Now your theta sub S is rotation along this angle right here. So if I can draw a line from this point up to that point, get this angle, and that's an angle equivalent to 2 times theta sub S. And I can apply my my analysis in terms of triangles, or analyze it in terms of angle, and I would be able to get what angle is this one. The problem with using theta sub S plus theta sub P is that there's an absolute value right there, and it might lead you to error, because once you get a number, you don't know if it's positive or negative, or if it's giving you a number that makes sense at all. But again, don't use that. You only use it just to confirm your answers, but do not use it as a main method for you to calculate your theta sub S. That answers your question. I forgot to ask that question.
Yes, thank you, Professor.
Okay. Any other question? Okay, so I think it's 2:19. I hope we discuss more, but yeah, we can stop here. The important thing is everyone